Okay, guys, let's continue with the lectures. So at this point, let's perform some linear algebra manipulations. So we start with some simple manipulations. Let's create a matrix, 2 by 3 matrix. So you have 2 rows and 3 columns filled in with ones. And the second matrix we're going to construct is the matrix B with 3 rows and 2 columns. In this case, filled up with 2. This is introduced by this B variable, which is NP full 3 by 2 matrix with entries, all of them being 2. So if we perform this operation here, which is NP mat MUL, which means matrix multiplication, simply. The program is going to multiply the 2 matrices A and B. And it's going to construct the matrix C by the multiplication of A and B. So what do you expect here? You have to multiply a matrix with 2 rows and 3 columns with another one with 3 rows and 2 columns. What you expect is a matrix of 2 rows and 2 columns. And this is what you get, actually, the multiplication of the 2 matrices. Another way, let's construct this NP identity 3 by 3 matrix, which is the identity matrix in 3 dimensions. This is the 3-dimensional matrix, identity matrix. So if you want to calculate the determinant of this matrix, what you have to do is to use this NP module command, which is NP linear algebra. This is what it stands for, determinant of C1, and also the determinant of the matrix C, which is this one, the previous one. So if you just write down NP linear algebra lin alg det, the program is determining the determinant of the matrix. So let's also make some algebraic manipulations with arrays. So the first array is A, which is an NP array with components 1, 2, 3, 4, and also the array B. If we use the command vstack, what we're going to do is we're going to stack vertically A and B. So C1 is NP vstack. This is what you get, A and B. Now it's a matrix with 2 rows and 4 columns. Also, if we use the NP vstack command in this way, so what we actually doing is that we vertically stack A, B, and B twice. So what you get is this matrix here, which is a 3 by 4 matrix. We can do the same with horizontal stacking of vectors of NP arrays. So if you define A to be this NP array and B this NP array, what you have actually, if you want to stack them horizontally, you just enter NP H stack AB. So you stack A and B horizontally. If you write down, if you type NP H stack ABB, what you do is actually you stack A alongside B, and then finally you also stack B in this chain. And this is what you get. Careful here, H stack. So another important command from NP module, from the NP module, is how to extract data from some text. This might be an Excel exported file in TXT format, with the delimiter being a specific form. It can be a semicolon or a comma. I use the comma here. It's important to include the data TXT file in the same folder that Python performs the calculation. So where you have actually this file here, I have it in my documents, the data TXT file has to be in the same folder. So if you extract the data from it, okay, possibly I don't have it here. Must have missed it. But in this way, anyway, because I changed my laptop, I don't have this data txt here. In this way, you can extract data from some txt file. I can create, just pause the presentation, and I will create a data txt file, and then. So let's proceed with playing with data. In Python, it's very simple to play with large data. Actually, you can enter the data from a plot, from a figure, from a JPEG figure. So you have a large amount of data included in this photo. I'm going to show you later on how you manipulate data, but let's play with some small data first. So I introduced the matrix with NP-array A. So this is the first NP-array, and the second NP-array is B. So I'm going to generate an H stack, a horizontal stack of AB, and a horizontal stack of AB with BB. So basically what you have is here. So let's define this name, this horizontal stack, with C2. So at this point, I want to find the entries of C2, which are larger than 50. So if I press C2 larger than 50, it returns to me that this is false everywhere. If I want to print the data of C2 with values that are larger than 5, I just enter C2, and with this square brackets C2 larger than 5, it just returns the values of the C2 entry, the C2 NP-array, which are the values are larger than 5. Also, you can find which column has values larger than 5. If I print NP any with C2 larger than 50, you find false. You don't have such a large value in C2. But if I print NP any with C2 larger than 5, then you have entries that are correspond to this value, that are larger than 5. Also, some very useful condition in order to have a combination of condition is this symbol here, which means end. So if I want values with C2, with entries in C2 which are larger than 3 and smaller than 5, this is what I type here. A large parenthesis and two smaller parentheses with two additional conditions here. So in C2, you don't actually have values that are 4. So if I want to have a negative statement, so I want values that are not larger than 3, so smaller than 3, and I want values which are smaller than 5. Then if I type this with a larger parenthesis and the two constraints here included with the symbol end, what you get is this one. So, very important. NP arrays are going to be used in numerical analysis later on in these lecture notes and in these lectures. So, what we will have there is that we're going to have large NP arrays, which are basically data of any form. And in the end, I'm going to find the solution of a differential equation in a numerical way. And I want to find the values of the solution that I found, which satisfy a specific constraint. So if I start with an array, for example, R, ARR, I define the name as ARR. This is the NP array. What I want now is to get the elements of ARR, which are less than 16 and greater than 12. And also to find the exact location of the NP array for which these two constraints are satisfied. Less than 16 and greater than 12. With this kind of NP array, this is easy to see, which values are less than 16 and larger than 12. So I basically want 13, 14, and 15. This is easy to see. But imagine that you're going to have NP arrays with 1,000 or more entries. So it's not easy to spot the exact element, the exact entry of the NP array for which these constraints are satisfied. So in order to find this exact constraint, I just type np where. This is very useful command, np where, and the large parenthesis, which corresponds to the function here, to the np where function, array larger than 12 and array smaller than 16. So basically, if I run this, the Python program is going to return 2, 3, 4, 7, 10, and 8. These are positions of the NP array for which the two constraints are satisfied. So the first entry is the third one, the third element of the NP array ARR. The second entry is the fourth element, fifth element, eighth element, 11th element, and 12th element. Let's see this explicitly. So if I put ARR, for example, 2, it's going to print directly 13. So basically, Python returns the values of the ARR array for which these two constraints are satisfied. This is very important. So please have this noted. If I want to find an exact element of, an exact value of NP array, if it is contained in the NP array, then what I just do is I use NP where array ARR equals to, for example, 15. And the Python program is going to return the entries of the NP array for which satisfy this ARR equals 15. So this is a simple way just to find the exact element of an NP array, a large NP array, which is equal to specific value. Let's also see this is the same. The only new thing here is the AR shape, which is basically the shape of the NP array. So it contains basically 15 elements with ARR shape, but we already saw this in the previous lecture. So let's do some other extra algebraic manipulations with some NP array and NP modules, NP functions and commands. If we create, this is very useful. We're going to use it frequently in numerical analysis in various forms of physical problems. So if I type NP lin space, I basically create a linear space between 2 and 10 with step 1. So just a print here X, and also I'm sure this is one element between 2 and 10. And also C is another array which basically contains 20 elements between 2 and 10. So let's print this one. So here X is NP lin space, so it's just an element between 2 and 10, and NP lin space 2, 10 basically generates 20 elements between 2 and 10, including 2 and 10. This is very useful. I think I have in this lecture later on a very interesting example. So let's also see what's C. C here, psi, Y is an element with an NP array with 20 elements. This is what we expected because we generated this one here. So let's also play with some other tricks of NumPy. If I introduce a NumPy array, which is zeta here, and I use the question mark here before the variable zeta assigned to this NP array, Python is going to return what zeta is actually. So it says that it's an array. This is very useful also. If you have a large program and you forgot what a variable is, this is very useful. If you include a photo in the same folder that Python generates and operates, the kernel, then you can import the photo in a very simple way. I named the photo image.jpg. So from sky image, import IO, and I define the name photo, IO, IM read, and I extract the image JPG. And I also type photo. So this image is also not included, I guess, because I changed my laptop here. So let's skip this in this node. So I included the photo inside the folder that Python operates. It's different from this one because I took it from another laptop I'm using in my lectures. So I changed the image, photo shape, which is an array, doesn't have so many elements as this one. Anyway, so let's show the photo. This is the photo. This is actually the energy density of the primordial gravitational waves, and these are the sensitivity curves of several future experiments. So it's a physics plot. Okay, so I imported this photo named image with these commands here: plt im_show photo. Also note here that I imported matplotlib pyplot as plt. This is a unique way in Python, one of the interesting ways to create plots and show plots and photos. We're going to discuss this in a specific lecture by itself. So if I use matplotlib at this point and later on in this lecture, it's going to be just for demo reasons. I'm going to concentrate exactly on matplotlib in a specific lecture in a couple of weeks. So let's reverse the image. You can reverse the image by using this command here: plt im_show photo : -1. So this is the image inverted. You can also reverse the image in this way. We can also show specific parts of the image. Let's see if it works here. Yeah, it works. And also, you can use show the half the side of the image in this way. You can also apply functions to this array, to the image, basically. So you can find the answer here. I applied the NP sign on the photo. Basically, the photo is data. Photo is data. So basically, what you have here is a large amount of data, which is quite large, 4,000 or 5,000. These are very useful commands here. You can sum all of the elements of the photo. You can find the product, the mean, the standard deviation, the variance, the minimum of all elements, the maximum of all the elements corresponding to the NP array of the photo, the index value of the minimum, and the index value of the maximum. These are all commands that can be used to make data manipulations on the NP array corresponding to the photo. Let's see again once more the photo as data. So this is the photo here, a large amount of data. Let's find the elements of the photo, of the NP array corresponding to the photo, which is larger than 500. So you can say that nothing is larger than 500. Everything is false. Now we can define the new photo for which, let's say, it's the new elements are larger than 200. Basically, it will be the same because this photo has the same entries everywhere. Let's see the shape of the new photo. It has too many elements. So let's modify a bit photo. Just modified photo here, and let's see. It's very simple. It's a very simple photo. I should use maybe another JPEG figure. So let's find another one from the web. Let's say a car, Ferrari. Let's find this one. I like it. So I'm going to put it in exactly the same folder that my Python is operating. So I'm going to name this image. It's going to replace the other one. Yes. So let's take this one here as a photo. It's a nice, cool photo. Okay, this is a very cool photo. This is a Ferrari. So let's see the data contained in the Ferrari. These are not equal, as you can see. If I choose photo larger than 500, you have these results. Larger than 5, you have these. And larger than 50, you have perhaps some falses and some true. So let's keep the ones that are the elements that are larger than 200. And let's see the shape of the photo. So let's put now larger than, let's say 300. No, it's too large. 250. And the new shape is, I guess, smaller. Yes, much smaller. Let's put 270. Nothing. 160 and 50. And this new shape is exactly 27,901. Okay, we can also find which elements of the photo have exactly the value 255. And the new shape is even less than 27,901. And you can also play with the data corresponding to the photo here. So I'm going to replace np-where photo is the data contained to the photo larger than 200. I'm going to replace it with 255, while where it isn't larger, the element is going to be replaced with 0. So I replace elements larger than 200 with 255, and the rest are 0. So this is what you get. It still looks cool. It's a Ferrari. So we can also use alternative commands just to play with the data corresponding to the photo. So I'm replacing every element that is larger than 100 with 200. And in the other case, that this inequality is not true, I'm going to replace the element with 10. So let's see what we get. Another cool Ferrari. Okay, we have some extra commands and manipulations between arrays in NumPy. What you have here, I introduced X and Y. And if you want to have a scalar manipulation, which is defined in linear vector spaces between the two vectors, you just use this @ symbol. So you have basically a direct product of two vectors. Okay, let's find another one. what you expect here is to have 2 times plus 4. So basically, you should have 6 as a result. This is the dual of the vector of vertical vector 1, 2. And this is the ordinary vector 2, 2. This is an operation between dual spaces, dual vector spaces. You can also use maybe some imaginary numbers here, but no, I have to introduce this number here. I'm going to show you later on how you introduced imaginary numbers in this in Python. I'm not sure if this operation takes into account the true dual spaces, or it works with real spaces. I'm not sure. I haven't tried it. I just thought it, and I'm sharing my thought with you. Also, we can find the transpose of an array. So I define this array, which is a matrix with 2 rows and 1, 2, 3, 4 columns. So if I print zeta dot t, I basically find the transpose of the matrix zeta, matrix Z. Okay, so let's find it. The matrix Z is defined as this one. So the transpose is basically this one. If we apply this to the photo image we introduced earlier with Ferrari, it just finds the transpose of the image, the transpose of the data. So basically this is the transpose of the image. Also, you can sort an array. And this is quite useful too. Now let's proceed to the module SciPy. It's quite useful, SciPy by itself, mainly because in SciPy you have a lot of commands that can make you, enable you to integrate numerically and perform also other fancy manipulations of data. You can also find fast Fourier transformations of raw data. Let's start with integration first. Okay, so integration with SciPy is quite useful and powerful technique because it is based on a Fortran program, the QuadPack. It's very reliable. Let's define a simple function. We call it def f of x, and the function returns x to the power of 3. In SciPy, I have to use the lambda function in order to define the function in the context of SciPy. So from import SciPy integrate, I imported the integration now. I defined the function f as lambda he. This is very important in how the commands in SciPy are formed. This lambda is something like the name of the function, which is a function of he, of x. So x to the power of 3. I define a more complicated function. Lambda is a new function f, which has 4 different variables inside it. A times x squared plus b times y squared. So let's see how the SciPy integration model works with these 2 functions here. The command is SciPy integrate quad function, lower limit and upper limit. So it's basically very easy to perform the calculation, the integration. I define the function, import SciPy integrate, define the function f, which is lambda x, which is x to the power of 3, x to the power of 3, and SciPy integrate quad, the function f, from lower limit 1 to upper limit 2. So this is the result, and this is the error of the numerical integration. Notice that it is extremely small. It's basically 0. It's 0. And this is why this SciPy integrate quad command from the SciPy module is very reliable. It's basically a very powerful Fortran technique that integration module that runs in the background in the kernel. So this SciPy integrate is a very reliable integration technique. Let's make some linear algebra with SciPy. Similar in a way to the NumPy linear algebra operations, SciPy is also useful with linear algebra manipulations. So let's start with from SciPy import linear algebra, linalg, and also we import from NumPy the module NumPy. We also call the module NumPy. So I defined an NP array from the NumPy, and the linear algebra dot det is going to calculate the determinant of the matrix alpha, matrix A. And we can print the result here, making a string linear alts determinant of A. And the result is the determinant of the matrix A is -1. We can find the eigenvalues of a matrix. So I import SciPy again and the linear algebra command from the SciPy module, and also the NumPy I also call it. And let's find how you can easily find the eigenvalues and eigenvectors of a specific matrix. So you have a 2x2 matrix here, and you want to find the eigenvectors. The eigenvector is simply EV. So these are the eigenvectors of the matrix A. If you want to find the eigenvalue, then you just type EW. And this is the eigenvalues. So also with the SciPy module, you can also solve directly equations between square matrices. So you have an equation of matrix A multiplied by X, which is a vector, with 2 rows and 1 column, equals B some other 2x2 whatever matrix, square matrix, however, square matrix. So you define A, which is NP array 2x2 matrix, and you define B to be the vector 1, 1. So you basically have this matrix times X equals the vector 1, 1 with entries. So the solution of this equation here is basically linear algebra from SciPy, solve A, B with this order. The order plays an important role here. We can find the inverse of a matrix with SciPy. So I just call again from SciPy the linear algebra function, and I import NumPy also. And A is the inverse of the matrix A small with small. A capital is the inverse of the matrix A. And the A capital is equal to linear algebra, linalg, dot inverse, inv, of alpha. I can also print the result. The inverse of the matrix A is equal to alpha capital equals string. I make everything string in alpha, and we can print the result here. Also, this is the result. Also, we can verify that A times A small is equal to the identity matrix. You can see that easily. Indeed, if I print I, this is the identity matrix. And let's also see this explicitly. You can see that our result is correct. Also, we can make multiplication of square matrices with vectors. Okay, so this is B times dot. This is the multiplication of two matrices. Okay, let's see this. This is the multiplication of the two matrices. I can also print this explicitly, but this is the command how to multiply B with A. Okay, so let's proceed to the Fourier transformation, the fast Fourier transformation. This is not the functional Fourier transformation, however. This is very useful for taking Fourier transformations and Fourier coefficients from a large amount of raw data. So basically, you have the following calculation given a large amount of data with a sequence defined with a sequence n, and it contains exactly n capital elements, n length. The inverse of this array of this large amount of data is this one. Again, we have n capital elements, but in this case, what you actually have here as the first function is x of n. Let's consider a very simple signal, xn, with length 5, n capital equals to 5. So I import from SciPy the fast Fourier transform pack. This is a nice module of the SciPy module. It's a nice function of the SciPy module. And I import NumPy as the NP again. I define our initial sequence of data as NP array 1, 2, 3, 4, 5, and the Fourier transform, which is this one, of the elements xn, the fast Fourier transform, is defined by SciPy fast Fourier transform pack, FFT pack, dot FFT of x. So this is what I get. Must print this also. So this is what we get. This is the Fourier transformation of the entries x of n. I can also make the inverse and verify that what we found is correct. So the inverse of psi, of y, is SciPy fast Fourier transform pack inverse fast Fourier transform, not FFT, but IFFT inverse psi or y. And if I print this, this is exactly the sequence x of me. So we expect to find 1, 2, 3, 4, 5. Let's see this. And let's print the inverse of psi. It's this one. I wanted to separate it. That's just to demonstrate to you that this is 1, 2, 3, 4, 5. It also contains this complex parts, but these are all the 0. So basically, this is x, what we started with. 1, 2, 3, 4, and 5. Okay, this is quite interesting, but this is for analyzing large data. So let's skip this one, and let's proceed to the interpolation and also how to fit several curves with functions. So what we have here is we want to find a way used in a very elegant mathematical way to perform numerical integration and to fit several curves. Okay, so you have some raw data, and you want to fit this curve to find a curve, an interpolation of this curve in 1 dimension, 2 dimensional, 3 dimensional interpolation, just to see how to describe perfectly the curve. So how can we do this? You have an initial x array, which is basically from 0 to 6 with step 0.4. And this is quite large. And let's see how this x behaves. Let's find x explicitly. I want you to see this. So this is basically x. You can see that the step here is from 0 to 6, from number 0 to number 6, with step going with step 0.42 and this large number. So this is not accidental. What I want here is to find a 14-dimensional vector, which is x, and it contains values from 0 to 6 with this step. So you get basically 14 different elements contained in this X array. Also, I defined an element psi, y, with 14 elements contained. It's very important if we want to make manipulation between two different arrays, like plot the two arrays or to find interpolation or whatever. The dimensionality of the two arrays has to be the same. Also note here that 6 over 14 is exactly the step I used here. So basically I must have 14 elements contained between 0 and 6. Now, let's find the fit and an interpolation of this x parameter here. What can we do is, and this is a very important technique, I introduce a new step variable, a new array which contains the same values as here, however, with quite many elements inside, because I'm going to generate an interpolation of this curve here. If I plot this psi as a function of x, y as a function of x, then I'm going to have a specific curve, which is, let me show you, this one, the points. So what I want here is to find an interpolation of this curve corresponding to the points by guessing, by letting Python guess how to proceed from one point to another in a continuous way. So you do understand that the 14 points, the number 14 is quite small to make such an interpolation. What one needs is to have at least 100 or maybe 1,000 points, and let Python decide in a very smart way how to make this interpolation. So from the initial x and y NP arrays, I generate a new array with 100 elements from 0 to 5.57 and so on. The reason I chose a smaller number is that I don't want to find a number larger than 6, because the Python cannot interpolate with values larger than 6. And since I'm not very sure how this division becomes, how the division of 14 different elements from 0 to 6 arranges x, I can see that, of course. If I type x, I can see that it goes up to 5.5714, which is exactly this number here. So I want 100 elements from 0 to 5.57 and so on. I could choose a smaller number here, 55 maybe, but not a larger number than 5.57. Okay, because there's no data to interpolate there. So the new variable, which actually corresponds to the fit curve, to the interpolating curve of the curve psi y of x, is generated by the command inter p1d. So this is the linear interpolation. But first, let us plot the function y of x. So basically here, I plot this one. I can use import matplotlib.pyplot and I plot the variable y as a function of x here. I'm going to explain this later on. Okay, this is not very important. It has to do with the style. So the interpolation of this plot, with which are these linear points, has to fill in a very clever and formally correct way several points contained between the 2 points, every point here, and it has to decide what to do when the points are too far away from each other. So one way is to use one-dimensional interpolation, which is this command here, and I plot the interpolation I made with x of h, this xh, and linear interpolation function xh, and this has to do with the format. So the linear interpolation is simply this one. I can increase the number of points. I can make it 1,000. But as you're going to notice, it doesn't change much the result. You can play with this in principle. And you can check whether 100 points or 1,000 points is the sweet spot for you. So we can make also quadratic interpolation by using here the kind quadratic. So interpolation one-dimensional x of y of x, kind quadratic. PLT plot the result here. And the cubic interpolation is interpolation one-dimensional again, x, y, the kind is cubic. It's very important here, and I also plot the result. So I also plot the legend. I'm going to show you how this is done in Matplotlib. But for the moment, let's forget this and concentrate on this one and this one. So basically, if I run the program, I take 3 interpolations. The cubic interpolation is this one, the green dots here, not dots, these green symbols here. The dust curve is the quadratic. It's quite good, I would say. And the same applies for the cubic. And also the linear from the quadratic is not very, very different. But you can see that the quadratic is much more elegant. It's much more elegant. It adds curvature to the whole curve. So let's recall again what we do in order to make an interpolation, and the fitting of a curve also applies, can be used in the same way. I mean, scientifically, mentally the same way. So you have an initial amount of data, and y and x, and you want to find the interpolation of this curve y of x. So you generate a new linear space with 100 points from 0 to the maximum element of x, which is 57. And the interpolation needs basically x and y. So the linear interpolation function, the interpolation of x, y, is defined by interpolation one-dimensional x and y, kind linear or kind quadratic or kind cubic. So this is linear interpolation. So basically, after you obtain the interpolation, what you can do is just plot x, h, and the result of this action here. So I plot here x and linear interpolation as I defined here. I plot here x and the quadratic interpolation x under dash h, and also I can plot the cubic interpolation. So at this point, let me stop for some questions, and I resume the recording later on. Okay, let's continue. Let's see another example with this linear space. Okay, So this is the result we obtained with interpolation. What we have to do now is just to find how to fit a curve with polynomials or any other kind of functions. But before that, I'm going to show you something very useful in Python, which has to do with constants. And then we proceed to the generalization of the interpolation we created in the previous exercise. So SciPy constants find. I also called earlier the SciPy module. So let's find the SciPy constants. So you can see all the constants contained in Python. Basically, everything is here in various physical units and also in useful units in theoretical physics and particle physics, like natural units and so on. So let's specify a constant that we need actually. If we want to find any constant that contain Planck inside the constant, I just type here SciPy constants find Planck, and it returns several different constants that contain the word Planck. If I want to know the value of an exact constant, specific constant, I just type here SciPy constants, physical underscore constants, reduced Planck constant in EV, which is this one here, and note the square brackets I'm using here. So if I type this, I get 6.58 times 10 to the power of minus 16 in EV. Okay, times seconds. Also, if I want just a value in EV times seconds, I just put SciPy constants value, and it just returns the value without any units. So let's continue with the polynomial curves, curve fitting, which is this one here. Again, I import from NumPy NP and the matplotlib pyplot module, the PLT function, the PLT command. And if I introduce the NP array X and the NP array Y, I can make a polynomial fit of this curve here, X of Y of X, by using the NumPy module function NP polyfit of third degree. The value of the for the polynomial to be used as a source is, for example, you can create again a linear space with 100 points inside, and the polynomial fit of this curve here, you can also use the same command as previously, a little bit modified, like NP polyval, which is P and X underscore F. And of course, we can make the plots here of these two curves. This is a polynomial fit. And again, you can use a polyval polynomial fit just to extend the analysis you performed earlier with P, X, and Y. So this is what you get. This is the XY data plot, and this is the polynomial fit of third order. Let's make maybe a fourth order, let's say, or fifth order. So this is a fifth order polynomial curve. This is the fit. In the next lecture, I'm going to demonstrate how the matplotlib module works. So all these plots are going to be discussed in a very detailed way, and you are going to make fancy plots, even change the format of the letters here, the font, the size. You can make the grid disappear from the plot, and many other fancy manipulations of graphs. But this is the last command from NumPy that it's going to be quite useful. All the rest, for data analysis, you can find it in pandas for Python. I'm not going to dwell so much on this kind of data manipulation because I'm more interested on extracting data from specific physical problems, like, for example, dark energy problems or neutron stars, and I'm going to solve differential equations corresponding to these points. So data analysis is not my aim in these lectures. You can extend the first knowledge I gave you for this NumPy libraries just by typing pandas with NumPy, Python, NumPy data analysis, or something similar. YouTube. There are a lot of videos there. So let's stop this lecture at this point, and we can have a question session.